Hello and welcome again to my Physics Online video lecture series. Today's video is going to be about temperature. We're going to be discussing a few things about temperature. I'm not going to go necessarily into the zeroth law of thermodynamics, which just essentially says that if A and B are in thermal equilibrium with each other, and B and C are in thermal equilibrium with each other, then A and C should also be in thermal equilibrium, and that is one way that we have had in the past of defining temperature. Instead, I want to focus on temperature scales and maybe a little bit about what temperature is actually telling us from an energy perspective. So let's get into that, shall we? Because this video is covering a lot of ground already, I'm not going to really go too terribly much into the review of stuff. Let's just dive right into temperature scales. So temperature scales, basically we have three commonly used options. So this is how are we measuring temperature. Our options basically include the Fahrenheit scale, which is what we are used to in America, in the United States. If you ask, how hot is it outside? How hot is it what's the room's temperature right now? What temperature with the thermometer does the person have? There's also the Celsius scale, which most Americans also have some familiarity with from taking like a chemistry course or a physical science course, although we don't often use it to specify temperatures in everyday life. And then last but not least, there is the Kelvin scale. So what are each of these scales? Well, this one right here is the imperial unit, and originally it was defined in such a way that it was assumed that 0 Fahrenheit would be the coldest possible temperature, and then I believe they set 100 Fahrenheit to be like the average human body temperature, and it's gone through some revision. Boiling point of water, freezing point of water would be 212 and 32 degrees Fahrenheit. So there's a nice 180 degrees difference between those two things. That's another way of defining our scale. The Celsius scale is a metric scale. However, it is not the preferred SI scale for MKS because 0 degrees C is set as the freeze and melt point of water. So freeze, melt, water. And then 100 degrees C is basically the vaporization point. So evaporate or boil and condense. So at STP, or excuse me, at a standard pressure, so 1 atmosphere pressure. The Kelvin scale basically makes use of some of the more salient points of both of these other two scales. So 0 Kelvin is absolute 0. It's the lowest possible temperature, at least classically. Now, if you include quantum mechanics in, one of the things is, or if you use the laws of thermodynamics, it's actually impossible to reach absolute 0. So I said classically, but even thermodynamically, classically, you can't get all the way down to absolute 0. The delta T of 1 Kelvin is equivalent to a delta T of 1 degree C. Okay, so let's look at conversion factors. Okay, first of all, the Kelvin scale, how did we find absolute 0? Basically by taking and you can do this if you have the right equipment, but taking a sealed gas chamber and basically plotting temperature versus pressure on this gas chamber. And essentially you have temperatures in the Celsius range that are easily attainable, and you get some set of pressures. Well, it turns out that the pressure doesn't really hit zero until we hit some negative value down here on the temperature scale. And so wherever this intercept is, this is 0 Kelvin. But this right here, this temperature is in degrees C. The pressure could be in whatever units you prefer, maybe in pascals, maybe in torr, maybe millimeters mercury or bar, or whatever. Atmospheres, pounds per square inch. It turns out that this number here is negative 273.15 degrees C. So 0K is equal to negative 273.15 degrees C. Now going back to this Fahrenheit idea of 0 degrees Fahrenheit being the coldest possible temperature, we actually have had temperatures well below that just on Earth in nature, let alone if you go into space or go to other worlds, that kind of thing, or artificially made. So this brings us to the conversions. The temperature in Fahrenheit to Celsius is fairly straightforward. Let's say that I happen to have my temperature in Celsius and I want to convert it over to Fahrenheit. Well, I would basically have to multiply by 9/5, okay, and then I would have to add to that, so this is 9 degrees of Fahrenheit per 5 degrees of Celsius change. I would have to then add to that 32 degrees of Fahrenheit to get my temperature in Fahrenheit. Conversely, if I want to get my temperature in Celsius from Fahrenheit, I would take the temperature in Fahrenheit, subtract 32 degrees, and then multiply the entire result by 5 degrees C per 9 degrees F. Okay. What about Kelvin? Well, the temperature in Kelvin is the temperature in Celsius plus 273.15 Kelvin. You could, if you'd like to have a conversion factor attached to this, you could multiply by 1 Kelvin per 1 degree C, and then add to the whole thing your 273.15 Kelvin. And then likewise, to get to Celsius from Kelvin, you take your temperature in Kelvin, you multiply by 1 degree C per 1 Kelvin, and then from that you subtract 273.15 degrees C. Okay, so that's your conversion scales for temperature. Now, maybe a quick example is warranted here. So as a quick example, let's convert 68 degrees Fahrenheit to Celsius and Kelvin. So this would represent T Fahrenheit. Process to get into Celsius, T Celsius is T Fahrenheit minus 32 degrees Fahrenheit times 5 degrees Celsius per 9 degree Fahrenheit. Okay, so 68 minus 32 is 36. That divided by 9 is 4. That times 5 is 20. So this is 20 degrees C. This is what's sometimes called room temperature, by the way. And this is kind of when we say we expect something at room temperature, we expect 20 degrees C. To get into Kelvin, you use the temperature in Celsius, you multiply by 1 Kelvin per 1 degree Celsius, you add to it another 273.15. So we have 20 degrees C times 1 degree C per times a 1 Kelvin per 1 degree C. We add 273.15 Kelvin. We get a temperature in Kelvin of 293.15 Kelvin. So those are the answers to this basic example. So what is it that temperature is actually telling us? Well, there's a number of definitions, but one definition is how much kinetic energy the average molecule in the thing that we've taken the temperature of has. So temperature relates to average kinetic energy. So the temperature is average kinetic energy of the particles in the sample. That typically means of the molecules in the sample. But depending on what kind of sample you have, that could actually be applied to atoms, or even in some things like plasmas, that might be the electrons. In any case, how is it that temperature is related to this average kinetic energy? Well, if you use 3/2 times the Boltzmann's constant times the temperature, then you get the average kinetic energy of the molecules. So I will use a K with an E subscript here. And you'll recall that K with an E subscript is 1/2 times the mass times the speed squared. So it's the average of the speeds, of the square of the speeds. And I should note that when we say average kinetic energy, we specifically mean translational, not rotational. So not rotational here. There is not a 1/2 I omega squared term to go with this. The Boltzmann's constant, this term right here, this is called Boltzmann's constant. It's named after, well, Boltzmann. And it has a value of Kb of about 1.30 times 10 to the minus 23 joules per Kelvin. Okay, you can approximate it as 1.38 or 1.381 times 10 to the minus 23. It has more digits after that. It is a fundamental constant of the universe, and it converts between this kinetic energy and this temperature for a gas that has 3 degrees of freedom. It should be perhaps now made more apparent why it is that we care about absolute zero or having an absolute zero value on our temperature scale, because this equation says if I double my temperature, I also double my average kinetic energy. But what temperature do I have to double? I obviously have different results if I say that I have a temperature of 68 Fahrenheit or 20 degrees C or 293.15 Kelvin. So which of these three numbers am I actually doubling if I want to double the temperature? Well, it turns out that it's this last number here. So the temperature in this equation must be in Kelvin. That also will apply later to all of the gas laws. When we say we double the temperature of something, we mean we're doubling the Kelvin temperature, not the Celsius or the Fahrenheit temperature. Let's do a quick example of using this equation to get the average kinetic energy from the temperature. We'll forego finding the average speed of the molecules at the moment because there's actually some more physics that we need to do in order to figure out this m term, the mass. So this is, we need to know basically how to get the mass of a molecule. So this right here would be your mass of a molecule. And if there is more than one type of molecule, then this bar really properly extends over both the M and the V within your system. So for example, in air, where you have a mixed gas that has nitrogen, oxygen, and a bunch of other trace molecules, ozone, etc., then you really would be doing the equivalent of mass times speed squared for each molecule, then averaging all of those together to get this term. So how do we get the mass of molecules? That's for a different video when we talk about moles. So here's a quick example. What's the average translational kinetic energy of air molecules if the air temperature is 30 degrees C? All right, well, the average kinetic energy, which I'm using as a bar over the K sub E, is 3/2 of the Boltzmann's constant times the temperature. But that temperature needs to be converted into Kelvin. So we could say T sub K. So this is 3/2 of the Boltzmann's constant times Tc plus 273, or maybe I should do this properly, Tc times 1 Kelvin per 1 degree C plus 273.15 Kelvin. This right here yields an average kinetic energy of 3/2, we'll say approximately 3/2 times 1.38, we'll just round it off there, by 10 to the minus 23 joules per Kelvin. Note that I'm going to have joules per Kelvin. The Kelvins will cancel. Times 20 degrees C by 1 Kelvin per 1 degree C plus 273.15 Kelvin. So this entire part of it, the temperature, is 293.15 Kelvin, which is also what we converted earlier. So now we can throw this into a calculator and do some multiplication. I get as a result that the average kinetic energy is about 404.547 times 10 to the minus 23 joules. Rounded to three significant figures, this would give us an average kinetic energy of approximately 4.04 times 10 to the minus 21 joules per molecule. So if you want to include the per molecule, you can do that as well within the units. So that's joules per molecule. Alright, that's it for today's video. Hopefully you have a little bit better of an understanding after watching this of temperature, or you've at least learned something about temperature in watching it, and thanks for watching.